This is the lecturette for section 14.6, talking about reaction mechanisms and catalysis. In this section we're going to look at elementary steps and reaction mechanisms. Reaction mechanisms are a series of unique chemical events called elementary steps. And we'll relate reaction mechanisms to rate laws, and then we'll look at some more complex mechanisms, and finally we'll talk about catalysis. So here's an idea of what a mechanism is. This first step, this will be called step 1, involves this water here, and the idea is this electron pair makes a bond there, and that electron pair becomes a lone pair there, and you make this product. So it's a unique chemical step, where mainly involving a bond formation between that oxygen and that carbon. That same species then undergoes a second step where it reacts with a second water. And this is actually an acid-base reaction because the water comes by and takes that hydrogen off and ends up making this hydronium ion and leaving that species without the hydrogen on it. So that's step 2. That's the second step. And then finally this species, the hydronium ion floats away, this species undergoes a rearrangement where it breaks this carbon-chlorine bond and goes to make 2 separate products there. So that's step 3. And so the idea is the reaction occurs in a series of 3 steps. The original starting material here reacts with a water molecule, making this species, which only lasts for a little while, and that's called an intermediate. And then that species reacts with a water molecule, making a second temporary species, a second intermediate, and that second intermediate finally goes on to make the final products of the reaction. So reaction mechanism is a pathway by which the reaction proceeds to get from reactants to products. It's the detailed chemical step-by-step pathway the reaction takes. And so each reaction mechanism is a series of discrete chemical events. Each of those is called an elementary step. Those steps are usually unimolecular or bimolecular. Let's go back for a second. In this first step, 2 things react. So that's a bimolecular step. In the second step, 2 things react. That's a bimolecular step. In the third step, a single molecule is reacting, so that's a unimolecular step. And almost all steps are either unimolecular or bimolecular. The overall reaction is the sum of those steps, which makes sense. The elementary steps, each elementary step goes at its own rate and has its own rate law. And the rate of the overall reaction is the rate of the slowest step, and that's called the rate determining step, often written RDS for the rate determining step. Okay, so let's talk a little bit about labels we use for things. Reactants obviously are things that are on the left side of the equations. Products are on the right side of the equations. For an overall reaction, the overall reaction is the sum of the elementary steps. An intermediate is a species that's formed in one step and then used in a later step. We saw that 2 of those in the previous example. A catalyst, which we've not seen yet, is used in one step and then reproduced in a later step. And so we'll see examples of that as we go along. So let's look first at just how we get overall reactions from elementary steps. So here's 2 elementary steps, step 1 and step 2. To get the overall reaction, what you do is you add everything on the left and everything on the right, but cancel things that are on both sides. So here we have an O3 and O3. We have an oxygen on the left. On the right, we have an O2, 2 O2s, another oxygen on the right. So this oxygen will cancel because it's on both sides. And so we end up with 2 O3s on the left, and that goes to make 3 O2s on the right. So that's the overall reaction. So if we were doing, say, stoichiometry, we would just look at that, and that's fine. But in fact, there are free oxygen atoms that exist part of the time during that reaction, but are never they're not used as reactants and not produced as products. They're intermediates that exist just for a little while. So let's look at a couple of examples where we search for both the overall reaction and intermediates and catalysts. So first of all, let's look for intermediates first. An intermediate is something that's made in one step and then used up in a second step. And that's one of the things we'll cross out on both sides. So in the first step, notice we make N2O2. And then we use the N2O2 in the next step, so that gets canceled. So that's an intermediate. N2O2 is one intermediate. And then in the second step, we make an N2O, and we use that N2O in the third step. So the N2O is made and then used, so that's a second intermediate. And let's see if there's anything else that's used, that's made, and then used up. Nope, it's not. So then what we do is we add everything on the left that's left. So 2 NOs, gas, plus 2 H2 gas, one here and one here. And that goes to make N2 gas plus 2 waters. That's our overall reaction. So this part here becomes that. Now, are there any catalysts? There are not, because there's nothing that's used in one step and then reproduced later on. This reaction, though, does have a catalyst. So let's look first for intermediates, and there's one. In the first step, we make this IO minus, and then we use that IO minus in the second step. So the intermediate is IO minus, aqueous. And catalyst, I'll cross that out for when we do the activation, the overall reaction. Catalysts, notice the I minus is used in the first step, but then produced in the second step. So I minus is a catalyst. So it has to be there for the reaction to occur, but it's not produced and it's not really used up. So if you put in a little bit of I minus, it gets used, but then it gets regenerated. So it gets used over and over and over again. So that means that this I minus can go back and react again. For the overall reaction, we'll have 2 H2O2 aqueous. That's these two here. Those two have canceled. That and that have canceled. So we go to make 2 H2Os, liquids, plus an O2 gas. And that's our overall reaction. Now we're going to talk a little bit about how intermediates are related to our reaction coordinate diagrams. What happens is if you have a reaction that happens in a single concerted step, so this is a single concerted elementary step. And concerted means that bond making and bond breaking happens at the same time. So we have this fluoride coming in here. We have this chloride popping off. And what happens is, as the reactants come together, they go up to this activated complex, which is also called a transition state, which is that species right there. And the idea is that species never exists in and of itself. It doesn't last for any amount of time. It's just the high energy point along the way of going from here to here. And so it's a single step. The energy to get from here to here is the activation energy, and the energy that goes there is the energy going down from the activated complex to the products. In the case of a two-step reaction, a true two-step reaction, you actually make an intermediate. And so in this case, the IO minus is an intermediate. And the idea is that the intermediate is lower in energy than the activated complex to get to it. So there's an energy well where the intermediate lies, and in our case here, that's the IO minus. So the IO minus gets formed. It's in this little energy well. It's not going to last long because it's going to pop over to that side there. But it lasts long. It lasts a little while, so it actually exists in solution. And sometimes you can actually observe it experimentally. Now we're going to talk about mechanisms and rate laws. And the idea is that you don't really use mechanisms to predict rate laws. What you do is you use rate laws in order to confirm or try to confirm or rule out mechanisms that you propose. You always know the rate laws experimentally and then try to figure out what the mechanism is from that. So, overall reactions and rate laws can't be linked. So if you know a balanced chemical reaction, you can't tell what the rate law is because of that. But for elementary steps, you can. For an elementary step, you can write the rate law based on what the products and what the reactants are. So if you just have a unimolecular reaction of A reacting to make B, or reacting to make some product, the rate law will be first order and have just A in it. If you have an elementary step that has A and B reacting, A and B will both be in the rate law. If you have two A's reacting, those will be in rate law. Very rarely you'll have three different things reacting, extremely rarely. And so all three would be in the rate law then. And when one thing reacts, that's a unimolecular step. When two things react, whether they're the same or not, that's a bimolecular step. And when three things react, that's a termolecular step. These are very rare and almost always involve solvent. That is, one of the molecules reacting will be a solvent molecule because there's lots of it. So it's likely that those three things could collide at one time. Now, so what happens is the overall rate is equal to the rate of the slowest step. So if we have a mechanism what we do is we propose a mechanism. So I bet this is how the reaction happens, and then we make an estimated guess about which of the steps will be slowest. So in this case, if we propose this mechanism here for hydrogen peroxide decomposing, catalyzed by I- ion, iodide ion, and we say the first step is slow, the rate of the first step is going to be given by K. I'll put a little 1 there, meaning it's the rate constant for step 1, times H2O2 times I minus. The rate of the second step is going to equal K2 times H2O2 times IO minus. If we're saying the first step is slow, the second step just doesn't matter because the reaction's going slow for the first step, and by the time these get made, they're going to react really, really fast. So we don't care about this at all if this is the slow step, if step 1 is the slow step. And therefore, the reaction rate law proposed that we expect proposed for this mechanism would be a reaction that's first order in hydrogen peroxide and first order in iodide ion. So that's the way it works. The way it works in terms of how this is really used is what you do is you propose mechanisms. Once you have a mechanism proposed, you do what we just did here, and you say, okay, if that's the mechanism, this is what the rate law will be. And then you compare that rate law to the experimentally determined rate law, which we talked about in the last previous sections. And what happens is, if the two agree, that mechanism that you proposed might be right. It might not be right, but it might be right. If the two disagree, the mechanism you proposed is definitely not right. You never really can prove a mechanism for sure. You can just build up lots of evidence so that you're pretty sure. Okay, so let's look at an example. Here's a reaction of NO2, nitrogen dioxide, reacted with carbon monoxide to make nitrogen monoxide and carbon dioxide. The experimental rate law shows that the reaction is second order in NO2 and zero order in CO. And we propose two mechanisms. One mechanism says it's a single step and that oxygen just jumps over to there. It's a single step reaction. Not an unreasonable mechanism, perfectly reasonable. They bounce into each other, the oxygen moves over. Mechanism B is that the first step is, which will be the rate determining slow step, is that two NO2s react to make an NO3 and an NO. So an oxygen transfers from one NO2 to another. And then in a second step, the NO3 gives the oxygen to the CO, and that'll be a fast step. So for mechanism 1, we predict the rate will be equal to K times the concentration of NO2 times the concentration of CO, because those are the reactants in that elementary step. In mechanism B, we expect the rate to be equal to the rate of the slow step, so it'll be K times concentration of NO2, and there are two of them there, squared. And so what we conclude is that mechanism A, because that rate law, the rate law for mechanism A, does not match the rate law that we actually see experimentally, that's wrong. That's an incorrect mechanism. And so you discard that mechanism and say, it doesn't happen that way. This mechanism does have the same rate law, which means this one might be correct. Might not be, but it might be. So the way we talk about it is the experimental rate law supports mechanism B. Okay, one small note about catalysts and rate laws is that if you look at the overall reaction for this two-step mechanism, you see that the Cl is a catalyst because it's used in the first step and produced in the second step, and the ClO is an intermediate. And so if we think that the first step is the slow step and the second step is the fast step, we'll just presume that for now. The overall reaction is two O3s go to make, I left the 2 out, go to make 3 O2s. And so that's the overall reaction. Notice there's no Cl in the overall reaction. There's no Cl there. But the rate law for this step is equal to K times the concentration of Cl times concentration of O3. And that would be the rate law for the reaction. And so the key is that the overall reaction rate law, rate, is going to equal K times concentration of Cl times concentration of O3. And so notice that there's a species in the rate law that's not in the overall reaction. And that's okay. Catalysts appear in rate laws, but are not appearing in the overall reaction. Because they influence the rate, but they're not really an integral part of what is used or what is formed. They just help the reaction along. Now let's look at a much more complicated mechanism, one where the first step is not the slow step. In this case, we're going to have what's called a pre-equilibrium step. So the first step here is a Br2 molecule is going to split up into two Br atoms. And we're going to say that both K1 and K-1 are fast in both directions. And so the key is that in step 1, because this is fast, these two come into equilibrium. And when they come into equilibrium, the rate going forward is equal to the rate going backwards. The rate of the reaction is going to equal the rate of the slow step, which is the rate of step number 2, which is going to equal K2, the rate constant for that step, times concentration of Br times concentration of H2. However, notice that Br is an intermediate in the reaction. It's not one of the reactants. You're not allowed to have intermediates in the reactions. That's a key. You can't have an intermediate. I'm sorry. You're not allowed to have an intermediate in the rate law. It can be in the reaction, but it can't be in the rate law because you never measure it. You never know what it is. So what we have to do some manipulations to get rid of that Br. And the idea is that using our key, that the forward and reverse steps there are the same. That means that K1 times the concentration of Br2 is going to equal K-1. The -1 just means it's in the reverse direction. It's not a negative number. Times the concentration of Br squared. It's squared because there's a 2 there. So that rate going that way equals that rate going that way. And then we solve for the concentration of Br. Concentration of Br is going to equal the square root of K1 over K-1 times concentration of Br2. And therefore, the overall real reaction rate is now going to be, we're going to substitute that in. Now this doesn't have a Br in it, so it's going to be equal to K2 times the square root of K1 over K-1 times the square root of Br2 times of the concentration of the square root of the concentration of Br2 times the concentration of H2. So another way to write that would be K, because all of these just make a constant, times the concentration of Br2 to the 1/2 power times the concentration of H2. And that is the final rate law for that. And in actual complex reactions involving many steps, we often end up with very complicated rate laws, making this one even seem fairly simple. Now let's talk briefly about catalysis. Catalysts are used for two things. Everyone thinks of catalysts as speeding up reactions, and that's true. So here's an example of what a catalyst does, is it provides an alternate mechanism that has a lower activation energy. So an uncatalyzed reaction would have that activation energy. A catalyzed reaction would have that much smaller activation energy. And the concentration time curve would be slower for the uncatalyzed reaction and much faster for the catalyzed reaction. So that's kind of a diagrammatic example of how catalysts make things go faster. But another second important role of catalysts is to increase what's called selectivity. And the idea is very often in reactions you can have a reactant go to make two different products or even more than two different products. And the reason for that is that there's more than one mechanistic pathway available for that reactant to react, and it makes more than one thing, and that's bad. Because generally when you do a chemical reaction, you want to make one particular thing. You don't want to make mixtures of things. And so the uncatalyzed reaction has two different pathways with roughly the same activation energy, so you make lots of product A and lots of product B. And so your reactants are in the middle now. They're going that way and they're going that way at roughly the same rates, and so you've got two different products, and that's not good for you. The catalyzed reaction selectively lowers one of the activation energies. In this one, the one to the right. So you have a lot of molecules going that way, not very many molecules going that way. And so here you make mostly B is produced. as opposed to a mixture of A and B. Finally, we want to just touch on the fact that there are two different kinds of catalysts, homogeneous catalysts and heterogeneous catalysts. Homogeneous catalysts are molecules you put in solution. Molecules are ions you put in solution. They're in solution with the reacting species, or they're in the same phase. They're all in the gas phase together. They're all in the same phase. Heterogeneous catalysts are generally solids that reactions can take place on. And an example of this would be a catalytic converter in a car, which gives a metal surface to have nitrogen oxides react on. And so an example, a pictorial example of this would be an ethene molecule reacts with an H2 molecule. These two react to make an ethane molecule. And what happens is the H2 molecule comes down onto this metal surface, which I believe is platinum. And the fact that the hydrogens can bond to the platinum allows the hydrogen-hydrogen bond to break easily. Then what happens is the ethene comes down onto the surface, and it makes weak bonds to the metal. Once those are bonded, the hydrogens can sneak up and bond onto the carbons there. Once the ethane is formed, it can fall off the surface and go there. And so there are many, many reactions that happen by heterogeneous catalysis that are important in industry. The most important facet of a heterogeneous catalyst is that it's easy to separate from the reactants and the products. Because it's a solid, you just pull it out of whatever the reaction mixture is, and you've gotten rid of your catalysts. In homogeneous catalysis, you're stuck with the catalyst dissolved along with your products when you're done, and you have to go through fairly expensive processes to separate those. And that is the end of this section.